so now that's going. And I have the microphone there. Great. All right, so I might as well keep going from where I left off. Now that I've decided to start reading to YouTube. Okay. How high-level language implements arithmetic expressions, loops, and logical structures, machine level. Data representation, including signed and unsigned integers, real numbers, and character data. How to debug programs at the machine level. The need for this skill is vital when you work in languages such as C and C++, which generates native machine code. How application programs communicate with the computer's operating system via interrupt handlers and system calls. How to interface assembly language code to C++ programs. How to create assembly language application programs. Okay, so this is all what I'm going to be learning. How does assembly language relate to machine language? Machine language is a numeric language specifically understood by a computer's processor, the CPU. All 86 processors understand a common machine language. Assembly language consists of statements written with short mnemonikers such as ADD, MOV, SUB, and call. Assembly languages has a one-to-one relationship with machine language, such as assembly language instructions correspond to a single machine language instruction. How do C++ and Java relate to assembly language? High-level languages such as Python, C++, and Java have a one-to-one relationship with the assembly language and machine language structure. Cool. Nope, didn't want to do that. Okay. How do I get this to be like on the actual screen? Isn't there a way to pop this? Nope. I thought there's supposed to be a way to pop this out so I can see it. Let me see here. What's this called again? OBS. OBS chat overlay. How do I add my chat to my stream? However, you can display chat overlay from a third-party alert provider, which are then embedded in the stream using a browser source. Overlay to OBS. Open a browser into the stream element website and log in. Select stream tools. Overlays from the stream element page menu. Create a new overlay. Set the overlay resolution to match that of your stream and click start. Name the overlay chat window and click save. Open a browser to the stream element website and log in. Select streaming tools. How to get chat on stream OBS. Get your chat URL from the provider. Open the OBS and click on the plus icon at the bottom of the OBS software as shown in the figures. Open the OBS, click on the plus icon at the bottom of the OBS software as shown in the figures. Click on the browser button. Type a name for your chat and click on the OK button. Okay, so open the OBS and click on the plus icon. these plus icons? Maybe one of these ones. Video capture, VLC video, window capture. What did it say? It said, click the plus icon on the bottom of the OBS software. As shown in the figure, click on the browser button. Okay, where is the browser button? Go chat log. Okay. Just hit OK. Supposed to do something else. Click on the browser button, type a name for your chat, click on the OK. Click here, browser, click, set height and width, chat provider, URL. File, add chat to OBS. What? What's step one? Is these step ones? Developer settings, monitor chat. Open chat room. Get the chat URL from the provider. First step is get the chat URL from the chat provider. Interface as if you were able to open the chat in a new window. Get the URL with the browser. That simple chat account from here. Chat URL from YouTube. It seems you like looking for the URL or link related to chatting on YouTube. However, YouTube doesn't have a specific chat URL in the traditional sense. Referring to live chat during a live stream or premiere on YouTube, you can find it on the right side of the video player. For general comments and discussions, you can find the comment section below the video. Keep in mind that YouTube interface may change over time. So then maybe I need to go to YouTube. I got my account. May change over time. So then maybe I need to go to YouTube. Oh, this is very meta. I got my account. Maybe just this, pop-out chat. May change over time. So then maybe I need to go to YouTube. Oh, this is very meta. Close, close. I don't need that. Go back to this pop-out chat page where I was studying from. Oh, this is very meta. Close. I don't need that. And now I have the YouTube. Go back to. Isn't that nice? Go back to this pop-out chat page where I was studying from. Oh, this is very meta. I could just keep this over here then. Close. I don't need that. And now I have the YouTube. Go back to. Isn't that nice? And can I close this? Does that? Oh, wait a minute. Now I don't have my. Okay, so I do need that open. Okay, go back. Go back to this. Find where my stream is. So that would mean that I would need to start a stream every time though before I can get to the chat. Okay, go back. And now I need to mute this. Right? Oh, what just happened to the chat? There it is. Okay. Oh, there it is over here too. Well, now I'm extra confused, so I don't need that there. Maybe I didn't need that? Okay. Let's try closing out of this again. Oh, it's still there. Okay. I just need to make sure not to click around too much. Can I fix it there? Interesting. Nope. All right. Well, cool. At least now I figured out how to put that there. Your guard, your privacy, abide by our community guidelines. Yeah, no problem. All right, I'm going to continue studying. How do C++ and Java relate to assembly language? High-level languages such as Python, C++, and Java have a one-to-many relationship with assembly languages, and machine language, a single statement in C++, for example, expands into multiple assembly language or machine instructions. Most people cannot read raw machine code, so in this book, we examine its closest relative assembly language. For example, the following C++ code carries out two arithmetic operations and assigns the result to a variable. Assume x and y are integers. Integer y, integer x equals y plus 4 times 3, which would be 3y plus 12. So you minus the 12, divide by 3, so okay. Is the equivalent translation to assembly language. The translation requires multiple statements because each assembly language statement corresponds to a single machine instruction. Move, example y, move y to the EAX register. Okay. Move, add, move 3 to the EAX register, multiply EX by EBX. Oh, that's how it looks when you have to do that? Oh, wow. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 characters turns into all these words. That's crazy. Registers are named storage locations in the CPU that hold intermediate and relative intermediate results of operations. The point of this example is not to claim that C++ is superior to assembly language or vice versa, but to show that their relationship. Is assembly language portable? A language whose source programs can be compiled and run as a wide variety of computer systems is said to be portable. A C++ program, for example, will compile and run on just about any computer, unless it makes specific references to library functions that exist under a single operating system. A major feature of the Java language is that compiled programs run on nearly any computer system. Assembly language is not portable because it is designed for specific processing family. There are a number of different assembly languages widely used today, each based on a processor family. Some well-known processor families are Motorola, the 6800, or the 86 Sun, SPARC, VAX, and IBM 370. The instructions in assembly language may directly match the computer's architecture, or they may be translated during execution by a program inside the processor known as a microcode interpreter. Why learn assembly language? If you're still not convinced that you should learn assembly language, consider the following points. If you study computer engineering, you may likely be asked to write embedded programs. They are short programs sorted in a small amount of memory in single purpose devices such as telephones, automobile, fuel and ignition systems, air conditioning control systems, security systems, data acquisition instruments, video cards, sound cards, hard drives, modems, and printers. Assembly language is an ideal tool for writing embedded programs because of its economical use of memory. Real-time applications dealing with simulations and hardware monitoring requires precise timing and responses. High-level languages do not give programmers exact control over machine code generated by compilers. Assembly language permits you to precisely specify a program's executable code. Computer game consoles require their software to be highly optimized for small code size and fast execution. Game programmers are experts at writing code that takes full advantage of hardware features in a target system. They often use assembly language as their tool of choice because it permits direct access to a computer's hardware, and code can be hand optimized for speed. Assembly language helps you gain an overall understanding of the instructions between computer hardware, operating systems, and application programs. Using assembly language, you can apply and test theoretical information you are given in computer architecture and operating system courses. Some high-level language abstract their data representation to the point that it becomes awkward to perform. Low-level tasks such as bit manipulation and in such an environment, programmers will often call subroutines within assembly language to accomplish their goals. Hardware manufacturers create devices driven for the equipment they sell. Device drivers are programs that translate general operating systems commands into specific references to hardware details. Printer manufacturers, for example, create different MS Window devices driver for each model they sell. Often these device drivers contain significant amount of assembly language code. Are there rules in assembly language? Most rules are assembly language are based on physical limitations of the target processor and its machine language. The CPU, for example, requires 2 instruction operations to be the same size. Assembly language has fewer rules than C++ or Java because the latter use syntax rules to reduce unintended logic errors as the expense of low-level data access. Assembly language programmers can easily bypass restrictions characteristics of high-level languages. Java, for example, does not permit access to specific memory addresses. One can work around the restrictions by calling a C function using JNI, Java Native Interface classes, but the result programs can be awkward to maintain. Assembly language, on the other hand, can access any memory address. The price of such freedom is high. Assembly language programmers spend a lot of time debugging. So, not too many rules, but you should follow the rules if you don't want to debug a bunch. That's what I'm getting out of it. Okay, assembly language applications. In the early days of programming, most applications were written partially or entirely in assembly language. They had to fit in a small area of memory and run as efficiently as possible on slow processors. As memory became more plentiful and processors dramatically increased in speed, programmers became more complex. Programmers switched to high-level languages such as C, Fortran, and COBOL that contained a certain amount of structure capability. More recently, object-oriented languages such as Python, C++, and C#, Java have made it possible to write complex programs containing millions of lines of code. It is rare to see large application programs coded completely in assembly language because they would take too much time to write and maintain. Instead, assembly language is used to optimize certain sections of application programs. for speed and to access computer hardware. Table 1-to-1 compares the additional of assembly languages to high-level languages in relation to various types of applications. That Roller Coaster Tycoon was written entirely in assembly language. That's just a fun fact. All right, that's how they managed to cut down on the size of it so much and still be able to maintain a program that ran with so many characters that would literally come and ride the rides and be able to handle all the roller coaster details. Ooh, let's see here. We have the type of application, the high-level language, and the assembly language. Type of application, commercial or scientific application, written for single platform, medium to large size. The high-level language is a formal structure, makes it easy to organize and maintain large sections of code. But in assembly language, minimum formal structure, so one must impose by programmers who have variety levels of experience. This leads to difficulties maintaining existing code. Okay. Hardware device driver. In a high-level language, the language may not provide for direct hardware access. Even if it does, awkward coding techniques may be required, resulting in maintenance difficulties. For assembly language, hardware access is straightforward and simple, easy to maintain when programs are short and well documented. So you can see a situation in which if there's a bunch of information, maybe higher language is easier. If it's having to do with hardware device specifically, you would want low language. Commercial or significant application written for multiple platforms, different operating systems. High-level language, usually portable. The source code can be recompiled on each target operating system with minimum changes. For the assembly language, however, must be recorded separately for each platform, using an assembler with a different syntax, difficult to maintain. Yes. Now then, for the embedded types, for the embedded systems and computer games requiring direct hardware access, may produce large executable files that execute the memory capacity of the device. Low level, ideal because the executable code is small and runs quickly. I have a suspicion, and I'm not too sure, but I have a suspicion that assembly language is good for like executable files, which is probably something that like hackers use a lot more. Like if you're going to write a program that's just going to activate and run based on the computer's hardware, you probably want it to be assembly language. The C and C++ languages have the unique quality of offering a compromise between high-level structures and low-level devices. Direct hardware access is possible, but completely non-portable. Most C and C++ compilers allow you to embed assembly language statements in their code, providing access to hardware details. Let me just quickly check. Can assembly language be used to hack people's computers? Assembly language, like any programming language, is a tool that can be used for various purposes, including legitimate and ethical ones, as well as malicious activities. Assembly language itself is not inherently good or bad. It depends on the intentions and actions of the person using it. Ethical and legal uses of assembly languages include writing low-level system software, device-driven and optimization-critical performance sections of software. However, using assembly languages or any programming language for hacking or unauthorized access to a computer system is illegal and unethical. Engaging in hacking activities such as Unauthorized access, data theft, or any form of cybercrime is against the law and is often lead to consequences. So yes. If you are interested in learning assembly language, programming language, I encourage you to do so with yes. Okay. Is assembly language designed to be a .exe file? Assembly language itself is not designed to be standalone executable file.exe. Assembly language is a low-level programming language that is specific to the particular computer architecture or processor. It's a human readable representation of machine code instructions that can be directly executed by a computer CPU. When you write programs in assembly language, you need to assemble it into machine code, which is a binary representation of the instructions that the computer CPU can execute. The process of converting assembly code into machine code is done by an assembler. Okay. What can assembly code do to the CPU on my computer? Instructional execution, control flow, data manipulation, system calls, optimization, interrupt handling, direct memory access. So, yeah, a lot of stuff that you would want to be able to control yourself. You wouldn't want other people to have control over. Okay. Section in review. How do assembly and linkers work together? How will studying assembly language enhance your understanding of operating systems? What is meant to be a one-to-many relationship when comparing a high-level language to machine language? This one that comes, okay. One-to-many relationship. We saw that not too long ago. But I guess too far back to just know. If I scroll over it, will it appear? Okay. How to simplest Java relation to assembly language. High-level languages such as Python, C++, and Java have a one-to-many relationship with assembly languages and machine language. A single statement in C++, for example, expands into multiple assembly languages or machine instructions. Most people cannot read raw machine code, so in this book we examine its closest relatives, assembly language. For example, the following C++ code carries out two arithmetic operations. Okay. So they're saying you write one line of code and it writes it into many lines of code, I think. Explain the concept of portability. I think what they're talking about with portability is that you're not you're able to easily show off the code and programs that you've been writing in to other places, other people. So a portable program is something that's like a higher language, which can easily be shown off and traveled through the internet. But the assembly language that we're learning here needs to be individually written for a specific situation, and I guess it's harder to share it. It's harder to take it places. Oops. Language portability. What are the trade-offs? Control versus portability is the primary one. Level 2, OS works on any computer running the same operating system. If an I/O device lacks certain capabilities, the OS will do its best to approximate the intended result. Level 2 is not particularly fast because each I/O calls must go through several layers before it executes. The primary disadvantage of using inline assembly code is its lack of portability. This is an issue when a high-level language program must be compiled for different target platforms. Inline assembly code that runs on an Intel Pentium processor will not run on an RISC processor. For example, okay. So yeah, it needs to be written basically for the computer that you want it to be used on. Okay. And based on the hardware that you want it to be run on. Give an example of embedded system application. Let's actually grab a few of these, and then we'll head on over here, and we'll ask for these examples. An embedded system application. An example of an embedded system application is a washing machine controller. In this scenario, an embedded system, a microcontroller or microprocessor, is responsible for managing the various operations of the washing machine, such as controlling the motor, monitoring the sensors for water level and temperature, and handling user input from the buttons. The embedded system runs a dedicated program that ensures the washing machine functions correctly. Device driver. Well, that's fascinating. All right. Device driver. A device driver is a specialized program or piece of software that allows the operating system to communicate with and control a specific hardware device. It acts as an interface between the hardware device and the higher level software application running on the computer. Device drivers are crucial for enabling seamless interaction between the operating system and the hardware components like printers, graphics cards, networks, adapters, and more. Type checking on pointer variables. Type checking on pointer variables is typically stronger, stricter in languages like C and C++ compared to assembly language. In languages like C and C++, pointers have associated data types. And the computer enforces type checking during compilation. This means that if you attempt to assign a pointer to a variable of an incompatible type, so trying to assign an integer to a string would not work, the compiler will generate an error. In assembly language, there's often an inherent type information associated with memory located or registers. Assembly language provides more direct access to memory and hardware, and type checking is the responsibility of the programmer. This can lead to potential errors if the program is not careful with the type of data being manipulated. It's a little confusing. So, does it result in an error or no? Like, both require is the responsibility of the programmer to know the syntax involved, essentially. That's funny to me. I guess, is it just not as apparent when you're working with assembly language? Maybe. 2 types of applications. It seems like the question got cut off, but assumes you're asking for 2 types of applications in general. Oh, let's see. Yeah. You're just looking for 2 types of whatever. Types of applications suited to assembly language. Two types of applications that might be better suited to assembly language than a higher level language are embedded system programming. Assembly language is often used in programming embedded systems where direct control over hardware resources is crucial, and the code needs to be highly optimized to specific microcontroller architectures. Okay? Device drivers. Writing device drivers, essentially the hardware components that require low-level control, can benefit from assembly languages. Device drivers often involve interactions with specific hardware registers and requires fine-grained control over hardware resources. High-level languages and direct access to printer port. A high-level language might not be an ideal tool for writing a program that directly accesses printer port because a high-level language are designed to provide abstraction from hardware details. Direct interaction with hardware ports, like printer ports, requires precise control over individual bits and low-level operations, which is more efficiently archived in assembly language. Yes, complexity and readability. Yeah, you're not going to write complex readability stuff for high-level programming to interact with electronic devices. That's what I'm understanding. Yeah, it's highly complex to write challenging code in such a low language. Assembling language is closely tied to specific computer architecture, so you're writing this code for specific hardware involved, specific devices, CPUs, things like that. Development time, developing large applications in assembly language is time consuming. Yeah, that single line of code, just adding and multiplying some things like this code down here, suddenly became like 8 lines of code. That's crazy. Knowing the specific assembly language corresponding to instruction set architecture, unfortunately. Yeah, okay, so it wanted me to recreate the output, which I didn't really look at too much, but it's this one. So, for integer y, move EAX, comma, y. Move y to the EAX register. Add EAX 4. Add 4 to the EAX register. It's just this right in here. Move EBX 3. Move 3 to the EBX register. Okay. I mul EBX. Multiply EAX by EBX. Why would anybody know that's what that means? Move X EAX. Move. Oh, and this is all lowercase EAX, which is definitely going to be different than capital letter EAX. Move EAX to X. So, get Y into position. Add 4 to that same position that Y is at. Move 3 to the EBX register, so in a different position. Multiply EAX by EBX, so that's why you're adding these two things first. This is now here off to the side. Now this is all being multiplied together. And then you're taking everything that you just made right there and saying this is all now X. Wow. And this is why I'm getting into programming now, where there's definitely much more higher level languages. I think it is fascinating. I'm sure there's some pretty significant things that people can do with this, but wow. Virtual machine concepts. An effective way to explain how a computer's hardware and software are related. Oh, let me get that. just nice, comforting. Have this off to the side. Effective way to explain how a computer's hardware and software are related is called the virtual machine concept. A well-known explanation of the model can be found in Andrew Tannenbaum's book, Structured Computer Organization. To explain this concept, let us begin with the most basic function of a computer, executing programs. A computer can usually execute programs written in its native machine language. Each instruction in this language is simple enough to be executed using a relatively small number of electronic circuits. For simplicity, we will call this language L0. Loser. Programmers would have a difficult time writing programs in L0 because it is enormously detailed and consistent purely of numbers. If a new language, L1, could be constructed that was easier to use, programs could be written in L1. There are two ways to archive this. Interpretation. As L1 programming is running, each of its instructions could be decoded and executed by a program written in language L0. The L1 program begins running immediately, but each instruction has to be decoded before it can execute. Translation: the entire L1 program could be converted into L0 program by an L0 program specifically designed for this purpose. Then the resulting L0 program could be executed directly on the computer hardware. Whew. Okay, yeah. So it sounds like essentially a metaphor. L0 in this case is maybe assembly language or binary. L1 is easier to comprehend. Eventually, they they write an L1, which is easier to make, and then they write it in such a fashion that it can be converted into L0. And then the L0 program now knows that it can convert like all L1 programs into L0. Yeah. Yeah. Rather than using only languages, it is easier to think in terms of hypothetical computers or virtual machines, as each level informally at each level informally we can define a virtual machine as a software program that emulates the function of some other physical or virtual computer. The virtual machine. I've played games on virtual machines before. VM1, as we will call it, can execute commands written in language L1. The virtual machine VM0 can execute commands written in language L0. Two different machines run two different codes. Whew. Virtual machine one, that's what it stands for, okay. Executes the machine in VM0, so VM1 can interpret, translate, execute on machine VM0. Machine VM1 cannot be radically different from VM0 because the translation or interpretation would be too consuming. What if language VM1 supporters is still not programmer friendly enough to be used for useful applications? Then another virtual machine, VM2, can be designed that is much easier to understand. The process can be repeated until virtual machine VMN can be designed to support a powerful, easy-to-use language. This sounds like linear algebra, which is what I'm studying right now. All right. Yes. So goes into the whole thing of how, computers can be developed, programming languages can be developed over time to be uh, more accessible to the public, easier to use, and then you can backlog and translate that into lower and lower levels until you're essentially working with binary. Yeah, so program written in Java language, translated by a Java compiler into Java byte code. Later, it is lower level language quickly executed on runtime by a program known as Java Virtual Machine. The Java Virtual Machine has implemented on many different computer systems, making Java programs relatively system independent. Specific machines. Let us relate this actual computer and language using names such as level 2 for VM2 and level 1 for VM1, shown in figure 1-1. A computer's digital logic hardware represents machine level 1. Above this is level 2, called the instruction set architecture ISA. It's the first level in which users can typically write programs, although the programs consist of binary values called machine language. Instruction set architecture level 2. Computer chip manufacturers design into the processor an instruction set to carry out basic operations, such as move, add, or multiply. This set of instructions is also referred to as machine language. Each machine language instruction is executed either directly by the computer's hardware or by a program embedded in the microprocessor chip called a microprogram. A discussion of microprograms is beyond the scope of this book, but you can refer to Nebium for more details. Assembly language level 3. Above the ISA level, programming language provide translation tight layers to make large-scale software development practical. Assembly language, which appears at level 3, uses short mnemonic such as ADD, SUB, and MOV, which are easily translated into ISA level. Assembly language programs are assembled in their entirely into machine language before they begin to execute. Ooh, look at that. Now we got 4 levels. These blocks keep on stacking. So now we're looking at high-level language, level 4. At level 4 are high-level languages such as C, C++, and Java. Programs in these languages contain powerful statements that translate into multiple assembly language instructions. You could see such a translation, for example, by examining the listing file output created by a C++ compiler. The assembly language code is automatically assembled by the compiler into the machine language section review. Come on. All right, so we have the in your own words describe the virtual machine concept. The virtual machine concept involves creating an abstraction layer between the hardware and the software. In this model, a virtual machine, VM, acts as an independently between the actual hardware and the programs running it. VM provides a virtual environment that abstracts away hardware details, allowing software to run consistently across different platforms. Nice. And then we have, why do you suppose translated programs often execute more quickly than interpreted ones? Because it's like speaking a foreign language. If you have to speak in a foreign language, then you probably have to interpret your words at some level, which can be a little bit slower and time consuming compared to just knowing the language and speaking it fluently. Let's see what they say. Translated programs often execute more quickly than interpreted ones because the translation process, compilation, converts the source code into machine code or an intermediate representation. This pre-processing step allows the program to be directly executed by the computer's hardware, whereas the interpretation programs are translated and executed line by line during runtime. True or false? When an interpreted program written in language L1 runs, each of its instructions is decoded and executed by a program written in language 0. True. False. So I got that wrong. But I could have sworn when interpreting program written in language L1 runs, each of its instructions is decoded and executed by a program written in language. So maybe it's not every time it's run. Maybe it's specific cases. Written in language level 1 runs. Each of its instructions is decoded and extracted by a program written in language 0, where L0 is typically a lower level language or machine code. Isn't that what we were just saying? Yeah, that's what I was initially saying. It's interpreted by a lower level language that was written by a lower level language, so that it could be read in a lower level language. Why did you say false? When an interpreted program written in language 1, level 1, runs, each of its instructions is decoded and executed in program written in language L0. And then it's like, no, because it's executed program is being decoded and executed by a program written in language 0. So it's hallucinating. It should be true. Explain the importance of translation when dealing with languages at different virtual machine levels. Explain the importance of translation when dealing with languages at different virtual machine levels. I suppose it would be at higher and higher levels. It'll take a little bit longer. Each time it has to translate down lower. So it'd have to translate down lower to a previous level. So essentially, I don't think that it can just skip down to the bottom. It has to be done in levels, which makes it slower. But a lot easier to write in. So you're definitely going to get things done faster. And then technically that'll be the quickest way to get a project done. Those programs written in high-level languages to be executed on diverse hardware architecture. The translation process ensures compatibility by converting source code. Okay. So their answer is that it's far more portable to write it at a higher level, but then it still needs to be translated down to be run at a lower level, no matter where it is that it's going to be run. At which level does assembly language appear in the virtual machine examples shown in this section? Assembly language appear in the virtual machine examples shown in this section. I believe virtual machine section is level 1, because it's then being translated down to the lowest level, binary. In a higher level than machine language, assembly language provides a more human, readable representation of machine code instructions, typically considered a low-level programming language. Yeah, so it's, I believe at one point it also said that the assembly language is like one level above machine language. I mean, at one point it was saying that it was a high level or something too, and it's like it definitely isn't. What software utility permits compiled Java programs to run on almost any computer? Um, Software utility permits. I don't understand entirely what it's talking about. Maybe CPU or something. Utility allows compiling Java programs to run almost any computer. It's a Java virtual machine. Oh. Okay, so a virtual machine for Java specifically is being run on computers to allow Java to be run on computers. Now, for virtual machine levels, we have the machine language, assembly language, high level language, and then machine independent language levels. I wonder if number 4 is like ChatGPT or something. Whoa, isn't that crazy? So now I am using this to explain the stuff. Programmers don't write applications in machine language because it's low level, platform specific, and challenging to read and maintain. Machine language in the virtual machine. Machine language is used on the lowest level, the virtual machine directly interacting with the hardware. Assembly language level translation. Statements at the assembly language level of a virtual machine are translated into statements at which other level? Assembly language level translation. Statements at the assembly language levels of virtual machine are translated into statements that are machine language level. Assembly language acts as a intermediate step between high-level languages and machine code, providing a human-readable representation of the machine instructions. Nice. Great. Now we're going to get into decimals and hexadecimals. Each number format or system has a base or maximum number of symbols that can be assigned to a single digit. They use current hardware, software, manual, hexadecimal numbers, digits 0 through 9, to the letter A through F to represent decimal values. 10 through 15 is quite common to use hexadecimal numbers. Binary integers. Cool. A computer stores instructions and data in memory as collections of electronic charges. Representing these entities with numbers requires a system geared to the concepts of on and off or true and false. Binary numbers are based 2 numbers. And that's why they scale up with power. Towards the left, bit on the left is called the most significant bit, MSB. It was already on a test. MSB, the most significant bit. LSB, I assume, means the least significant bit. Numbers of 16-bit binary number are shown in the following figure. So we have binary, 0 and 1, octal, 8, decimal, 10, okay, hexadecimal, 16. Binary integers, always starting from 0. It looks like hexadecimal goes from 0 through 9, which is typical decimal level, and then hexadecimal starts going with the alphabet for A, B, C, D, E, F. So the last 6 are in alphabetical. Binary can be assigned or unsigned. Assigned integer is positive or negative, and unassigned integer is by default positive. 0 is considered positive. When writing down large binary numbers, many people like to insert a dot entry, 4-bit or 8-bit, to make the numbers easier to read. Examples are 111.111.0.0011. Yeah. Yeah, okay, so when they're assigned, they're giving off these values, 2 to the 7th, 2 to the 6th, 5s, all these on 0. We already did this in class, where we had to add up numbers based on this, and I printed out a sheet so I can reference it, which looked basically exactly like this. Yeah, 8 plus 1 makes 9. Yep. So like the output of this code should be the number 9. To binary really define the integer by 2. And concentrate the binary bits from the remainder column to the table in reverse order. D5, D4. Produce binary because computer storage always consists of binary numbers whose lengths are multiples of 8. We fill the remaining 2-digit positions on the left with 0, producing 001, 001, 001. So that's 2, 4, 6, 8. Yeah, that is 8 places. Tip, how many bits? There's a simple formula to find b, the number of binary bits. So you need to represent the significant decimal value n. It is b equals ceiling, log 2 of n. If n equals 17, for example, log 2 of 17 equals 4.08, yada yada, which, when raised to the smallest following integer, equals 5. Most calculators don't have a log base 2 operation, but you can find web pages that will calculate it for you. Ooh, okay. Adding 2 binary integers proceeds a bit by bit. Yes, so 0, 0 equals 0, 0, 1 equals 1, 1 plus 0 equals 1, 1 plus 1 equals 1, 0. Not 10, 1, 0. Because it's essentially adding together to make 2, but there can't be 2. So you need a 0 in one space and a 1 in the second space. When adding 1 to 1, the result is 1, 0 binary, which is the decimal value 2. Yes, so that's what we get. 1, 1, 2, which is 0, 1, 1 comes down, 0, 0, 0, 0. Look at that, I was right. And then this would be 2 to the 0, so that's 1, 2 to the 1, which is 2. So add those together and you get 3. That's a 0. And the 2's, that's 3. So 2 to the 3, 2, 4, 8. 8 plus 3, 11. That's why you get 11. Beginning with the lowest bit on each number, bit position 0, we add 0 plus 1, yada yada, explains everything I just explained. Can only store 8 bits, will equal to, so the lowest 8 bits of the calculated value. Oh, that actually raises a good question for my homework, which is, when we were adding these things together and it did exceed a certain amount, should we have just kept adding to the bit, which is what I did, and I did double check with binary calculator, and that's what they did. But I'm also now wondering if maybe it's supposed to convert to hexadecimal after a certain point, in which case then I start using letters. I don't know. Basic storage unit for all data in an A6 computer is a byte containing 8 bits. Other storage sizes are word 2 bytes, double word 4 bytes, and quadruple words 8 bytes. The following figure, the number of bits is shown for each size. A word. So if I had to just have a string of names, each string would be 16 bits, I think. Ooh, 1 megabyte. 2 to the 20. So once you start breaking a million, you'll have a million bytes. You'll have 1 megabyte. And then you break through the millions to the billions places. You have 1 gigabyte. 1 terabyte is billion, trillion. Like I have 2 1 terabyte external hard drives. So I have over 2 trillion bytes that I can have access to. That's cool. That's fun. Whoa. Petabyte, exabyte, zettabyte, yottabyte. I hope to be as rich as a yottabyte one day. A yottabyte one day. Hexadecimal integers. Large binary numbers are cumbersome to read, so hexadecimal digits often offer a convenient covenant. Oh, what is this word? Convenient way to represent binary data. Each digit as a hexadecimal integer, representing the 4 binary bits, and 2 hexadecimal digits representing a byte. A single hexadecimal digit represents a decimal 0. 10 through 15, variables 1 through 5 shows how. Okay, let's just look at the table. Yeah, every 4 bits equals a number which in decimal, which represents a hexadecimal value. So each individual one is 4 binary. Yes, 4 binary values. Unassigned hexadecimal to decimal. Yes, 16 times 3. So yeah, all right. I have a cheat sheet for all of this. Just look up hexadecimal images and you can get that. Yep, and then you just add it all up, and that's the total. For unassigned decimals to hexadecimals. Uh-huh. 1A6, same algorithm used for binary integers in sections of 1.3.1 to convert from decimals. Okay, hexadecimal addition. Utility programs known as debuggers usually display memory addresses in hexadecimal. Interesting. I've seen those memory addresses, and I did not realize that it's a hexadecimal value, but that makes sense now looking at them. They always have a combination of numbers and letters. Fortunately, hexadecimal addition works the same way as decimal addition. Did I say fortunately or unfortunately? It sounds fortunate, but it does feel unfortunate. Suppose we want to add 2 numbers, x and y. Using numbers base B, we will numbers their digits from the lowest position to the highest. If we add digits x and y, xi and yi, reduce the value si. If si is greater than or equal to b, we recalculate si equals si mod b and generate a carry value of 1. Move to the next pair of digits, xi plus 1 and yi plus 1. We add the carry value to their sum. Ooh. Interesting. I have no idea what that means. 49a is the lowest digit position. 2 plus a equals decimal 12. Huh. Huh. Carries between 19 is greater than equals 16. Number base. We calculate 19 MOD. Did it specify what MOD stands for? Okay, I've got to take a break. This is